Right. So this video is going to act kind of as a supplemental lesson to what we've been dealing with in class, specifically my AP Physics C class regarding center of mass and the center of mass of continuous objects. Okay. Now, I will say I'm putting this video together specifically because I've had a couple of students ask me about a more advanced possible application of center of mass involving multivariate calculus. So that's what this video is going to cover. It's going to kind of cover the formulation that we would use in multivariate calculus to find the center of mass of a continuous object. And we're going to go through this problem and show you how to actually apply those formulations. Okay, so let me make this clear that if you're not interested in multivariate calculus and you're never going to touch it in your life, you don't have to watch this video. Again, this is purely supplemental. It won't be anything you'll be tested over or expecting though for the AP exam. Okay. Again, this is tailored to basically just a few students in my AP Physics C class. Okay. So AP1 in general physics, you don't need to do anything with this video. In fact, I would recommend clicking out now unless you really want to look and see what the horrors of mathematics can truly be. Okay, so here's the problem that we're going to go through and solve today. And I'm going to try my very best to use this problem as a way to kind of explain some of the formulation that is typically used in higher level calculus to talk about center of mass. Okay, so here's our problem. We're going to find the center of mass of the domain D that is bounded by the function y equals 1 minus x squared, okay, and the x-axis. So we were kind of trying to trace out some sort of domain or some sort of shape, and these are our two constraints for that shape. We have basically an upper bound of y equals 1 minus x squared, and the lower bound of our shape is just the x-axis. We know the x-axis, okay? And what we're going to assume about this domain, that we'll see what it looks like in a sec, we're going to assume that this domain is going to have a mass density of sigma equals y. Okay, so what you'll notice here is that we have a non-constant mass density. And when we have a non-constant mass density, that's typically when we want to use multiple integrals to find the center of mass of these objects. Okay, so if we have a constant mass density, we can usually stay with a single integral to solve for center of mass and related stuff. Okay, but when we have non-constant mass density like this, it's actually going to be a little bit easier if we're able to use multiple integrals. Okay, specifically a double integral in this problem. So before we even get started with the mathematics of trying to solve it, let's take a look at what our shape is going to look like with these constraints here. So the way I'm going to do that is by Desmos. Again, if you're on a computer and you're trying to make graphs of functions, I think there's no better way than Desmos. Easy to work. It's really simple. Okay. They also make a great scientific calculator to use on Google or whatever. So that I'm just throwing that out there. But let's look at what our shape is going to look like, our domain is going to look like with our given bounds. So we're told that this domain is bounded by y equals 1 minus x squared. Hopefully, non-surprisingly, looks something like this. Okay, it's a parabola flipped upside down essentially, and we're shifting it up to y equals 1. Okay, and we're told that our lower bound is going to be y equals 0. Okay, which is just our x-axis. Okay, so I've drawn this on here so that I can kind of visualize some important points about our bounds. Okay, and I'm going to go ahead and take this shape. So look at it for a second, see that it crosses through the x-axis at -1 and +1, and it gets up to a maximum height up here at y equals 1. So I'm going to take the shape. I'm going to go back to our little notebook here. I'm going to redraw that shape here. So if I draw a little tiny coordinate plane, okay, nothing too beautiful. Well, we said that our function is going to cross the x-axis at x equals -1, and it's also going to cross at x equals +1. And then we say in the y direction, it gets up to a maximum value of y equals +1. Okay, so again, this is our standard y and x axes. And then our function looks something like this. Oh, that is rough drawing, but work with me here. And so what we're imagining, what this problem is actually asking, is that if we treat our x-axis as our lower bound and this function as our upper bound, imagine that we take this space in between here and fill it in so that we basically have a plate of some area, and it looks something like this. And we want to know, well, where is the point of the center of mass of this shape, this two-dimensional shape? Okay, so again, in dealing with either discrete systems of objects in 2 dimensions or a continuous object in 2 dimensions like this, we have to fully describe our center of mass as a point in space. So some point of the center of mass, and that point would be represented by the ordered pair of our x coordinate of the center of mass and our y coordinate of the center of mass. Okay, pretty unsurprising stuff there. Okay, so now here's where I want to kind of introduce the higher level mathematical formulation for center of mass. Okay, if you were to go through a calculus textbook specifically and try and look up a problem like this, then you would find the formula of center of mass as being this. Okay, so if we wanted to find the x coordinate of our center of mass, you would find it written as this: capital M sub y over capital M. And if you wanted to find the y coordinate of your center of mass, a textbook would tell you something like this: capital M sub x over capital M. Okay, so this is kind of an interesting formulation here. Well, let's fill in a little bit of information about what these variables mean. This capital M without a subscript y or subscript x, we've dealt with this before in class. This is just basically the mass of our object. Okay. So again, we've seen this before with dealing with systems of discrete objects. This capital M will represent the total mass of all of the individual objects added together. And for a continuous object like this weird shape here, then this M is just going to represent the total mass of that object. Okay. Now, what we haven't seen before is this M sub y and this M sub x. Okay. And what these are defined as are the moment, either the moment about the x or about the y-axis, or so it's either when you have m sub y, it's the moment about the y-axis. When you have m sub x, it's going to be the moment about the x-axis. Okay, so great. We've established a couple of things about what these variables mean, but well, what is a moment? Okay. And in dealing with a problem like this, I'll go ahead and say this. This is a very, very mathematical approach to solving a problem dealing with center of mass. Okay. We're just dealing with a function, and imagine that in this function, this domain we're given, that we're filling it in and then we're trying to find the center of mass of that. So that's a very mathematical problem. We're kind of branching away from just purely physics. Okay. So I think in order to fully understand what you need to do in this problem, is we need to just go ahead and, well, explain it in terms of just mathematics. So I'm going to give you a mathematical definition of what a moment about the y-axis is. Okay, so let's start there. A moment about the y-axis is simply this: m1, x1. So imagine we're dealing with a system of discrete objects. Okay, like we did in class, we dealt with basically a triangle formulation of a bunch of different particles. Let's imagine that we're trying to talk about the moment about the y-axis of that system. Well, it would be m1 times x1 plus m2 times x2 plus m3 times x3 plus dot dot dot. Okay, we can sum up as basically as many particles as we have. Okay, that's our moment about the y-axis. Now, our moment about the x-axis, m sub x, would be m1 y1 plus m2 y2 plus m3 y3 plus dot dot dot. Okay, well, we've seen this stuff before. Okay, we've dealt with this in our kind of our easier equation for dealing with center of mass. We've seen this m1 x1 plus m2 x2, so on and so forth. We've seen that before. Okay, and we went about this, or we express this in a different way using summation notation. We basically wrote it as something like this, where we have m sub I, x sub I. That's what this whole thing here can be expressed as. And then for this, we can express it as this. Okay, so this summation, essentially what this is, well, it's the moment either about the y or x axis for either a given system of discrete objects or one continuous object like this. Now, why is it called m sub y if it's you're taking the x coordinates of each individual object? Well, the reason they call it like this is that you're going to reference your x coordinates for each given object using the fact that your origin is going to be the y-axis. Okay, so you're starting from your y-axis and then you're going along the x-axis, again, starting from your y-axis. That's why they call this m sub y. And then for your m sub x, you're starting with that your origin is the x-axis, and then you're counting up your y position from there. Okay, so that's why they use this notation. And again, it is confusing I don't. It's just one of those things. Oops. It's just one of those things that you will have to get used to. Okay. So now I need to add a little bit more space here. Okay, there we go. And so now this is again, I laid this example out to explain these moments here using a system of discrete objects. Okay, so a system of particles arranged in a certain way. That's kind of what this can be thought of as. But we're not dealing with a system of discrete objects. We're dealing with a continuous shape, again, described by this function in the x-axis. Now, what I try to get you to think about in class when dealing with continuous objects is think of it as being essentially a collection of a bunch of infinitely small pieces of the whole. Okay, so I want you to imagine that in order to find the total shape of this thing, we basically take a bunch of infinitely small pieces, each of them with an infinitely small mass, and add them all together. Okay, and well, so that would mean that we would have some. So let's say something like this: so that if we're to convert this now to a continuous object, we can now write. Oops, we can now write our summation as looking like this. We'd have, instead of m sub I, we'd have some dm, where again dm represents an infinitely small amount of mass. We have the same thing for this. Okay, well, that's great and all. We're saying that we're going to add up a bunch of infinitely small chunks with infinitely small mass at a bunch of infinite amount of x or y positions, and we're going to add them all up. Okay, and the way that we typically, when we're dealing with infinitely small things, the way we typically do that is with an integral. Okay, if we wanted to add up a bunch of small, infinitely small pieces, we typically do that with an integral. Okay, so now here's where I'm going to introduce what you might have seen before if you've looked into multivariable calculus and center of mass, is the calculus explanation for the moments. So our moment about the y-axis in calculus is written something like this. We'd have a double integral over our domain D of x times our mass density dA. Okay, so what this essentially is saying is, in order to find the moment about the y-axis, we need to, well, take the x position. This x represents where our infinitely small particles are located in the x direction, times, well, we have this mass density times dA. Okay, and where does this density come into play? Well, let me try and explain it like this. We've seen before that this sigma equals the mass of the object divided by the area of the object. Okay, and what we're trying to do with this double integral here is kind of mimic this summation here of taking infinitely small amounts of mass, multiplying it by its position, of multiplying it by that small chunk's position, and then adding them all together. We're trying to replicate that with this integral, using the integral because we are dealing with infinitely small pieces. Okay, so we need to try and get this to look something like this. Now we have the x here, which we see in this summation here, but this whole thing, we need to try and maybe find a way to relate it to the mass. And well, unsurprisingly, if we take a look at this definition for the area mass density, if I were to rearrange things a little bit, I would find that the total mass of the object equals our linear mass, or our areal mass density, times the area. Okay, and again, if we want to try and replicate this exactly like this, we have to deal with an infinitely small amount of mass, dm, and we could find that by taking the linear, or the areal mass density times an infinitely small amount of area. So that's where this comes into play here. We're just essentially trying to get this dm to show up in this integral. This is just a more robust way of writing it, because we have to deal with this mass density at some point in the problem. Okay, so hopefully that makes a little bit of sense of how this formulation comes to be. And then very similarly to this, our moment about the x-axis would be a double integral across a domain D of y times our mass density as a function of x and y times dA. Okay, so here's where we need to actually use this formulation to try and solve this problem. Try and find at what point can we consider all the mass of this object to be. At what point is the center of mass here? So first thing I want you to notice is that if you can make a problem like this simpler, you really probably should. And what hopefully you notice, maybe a little bit easier here if you look at it on Desmos, is that there is some symmetry in this shape. Okay, and I want you to see that there's a symmetry along the y-axis. Basically, if we cut this shape, down the y-axis will have basically a mirror image on either side. So what would that mean about something with our center of mass? Well, that would probably mean that our x-coordinate for our center of mass is going to be located right at x equals 0. Okay, because it's a nice symmetrical shape about the y-axis. We could assume that our x-coordinate of our center of mass, the center of mass would have to lie somewhere along the y-axis. So by thinking of just symmetry and what we would expect physically, we can already determine that our x-coordinate for our center of mass is simply 0. Okay. Now we have to find how high up do we have to go along x equals 0, along the y-axis, to find exactly where our center of mass is. Okay, so that's where we're going to need to use this formula here. So let's do it. Our y center of mass will equal our moment about the x-axis divided by our total mass. Okay, so let's start. We're going to have to actually determine what the total mass of this object is, and I'll show you how we can do that in a little bit. But let's start by just calculating the moment about the x-axis first, okay, because we just introduced the formulation for that. Let's go ahead and use it. So what we would say is this. Our moment about the x-axis for this shape will be the double integral, again, across the domain D of y times our mass density times dA. Okay, great. So I've just rewritten the equation we have up top. Let's go ahead and plug in some stuff that is specific to our problem. Well, first of all, we can plug in pretty simply, before we start figuring out our bounds for integrals and stuff like that, we can just go ahead and plug in what our mass density is. And if you remember from the problem up here, we're saying that our mass density is just simply sigma equals y. So we can go ahead and plug in y for sigma. Okay. And so what that would leave me with, I'm going through this very thoroughly, what that would leave me with is this integral here, or this double integral here. Okay. So now hopefully you've seen some applications of double integrals before and know how to work with them a little bit. I think those of you who have asked me questions about this, I think you have. So I'm going to go ahead and start filling in what this double integral would look like. Well, let's start. We need to find the bounds for our two integrals. Let's start by finding the bounds along our y-axis. Okay, so I'm going to now replace my dA with a dy dx. Okay, so imagine that why we make that substitution is that imagine that to find the total area of this shape, we're basically adding up a bunch of infinitely small squares together, and this or rectangles together, and the side lengths of that rectangle or that square would be dy and dx. To find the area, you'd multiply them together. That's why we can substitute this dA to a dy dx. Okay, so I'm going to put dy first because, well, we have, when we plugged in our sigma, our mass density, that we get just a y squared here. Okay, so we need to take our first integral here with respect to y, and then whatever we get, we're going to take the integral of that with respect to x. So we need to first determine what are the bounds along our y direction. Because again, we're going to integrate with respect to y first. So we need to determine the bounds in the y direction. Well, if we go back up here, we can pretty easily see that along the y direction, well, we're going to start at y equals 0, which is the x-axis. That's our lowest point in the y direction. And then this shape that we're tracing out, the highest point is always going to be this function, 1 minus x squared. Y equals 1 minus x squared. So our lowest point along the y-axis is 0. Then our highest point as we go along the shape will be the function y equals 1 minus x squared. So that means our bounds here, our lowest is going to be y equals 0. And then our highest up here is going to be 1 minus x squared. Y equals 1 minus x squared. That's how these bounds would work along this shape. Okay, so these are the bounds for our y direction. Now we need to determine the bounds for our x direction so that we can actually go through and compute this double integral. So, well, what are the bounds in our x direction? Well, we start our furthest point left in the x direction is just x equals -1. And then as we go along to the right, we're going to stop at x equals +1. So our bounds, pretty simply, are just going to be x equals -1 to 1. Okay, now this is a way that I would maybe, if you go on to do more stuff with double integrals, even triple integrals, it's usually a good idea to put somewhere in your bounds that you're talking about either y equals 0 or x equals whatever. Okay, you want to try and make it clear that these bounds are referring to y values and that these bounds are referring to x values so that you don't get them confused. Okay, so the way we go about doing double integration now is we need to first basically compute this thing right here. Okay, and what that would give us is if we were to go through and do that, I'm going to leave that to you to do this in excruciating detail. If I were to go ahead and compute this integral, I would get the following. I get 1/3 y third. That's just the antiderivative of y squared. And then we'd have to evaluate it from y equals 0 to 1 minus x squared. Again, say that this is talking about a y variable. Okay, so we're still keeping this integral here because we're going to have to actually take the integral of this whole thing here with respect to x. That's what this double integral is saying. Okay, so now if we were to go through and plug all this stuff in, again, I'm going to leave this to you to go through in the painful detail. I could take a 1/3 out because that's going to be a constant, and then I'd have this. Still keeping these bounds on this integral here. I'd have 1 minus 3x squared plus 3x to the fourth, I believe, minus x to the sixth, yes, times dx. Okay, that's what you would get if you were to evaluate this function here with these bounds. And then now we need to actually go through and integrate this. Okay, and I'm going to skip even more steps here. Again, I'm going to leave this to you. It's just integration at this point. We need to take the integral of this and then evaluate it with these bounds here, with our low bound being x equals -1, our higher bound being x equals 1. And if I were to do that, I'm just going to go ahead and skip to plugging in the numbers here. I would get something like this. And if you compute all of this, you should hopefully find that our moment about the y-axis, or the x-axis, sorry, is going to be 32 divided by 105. Okay, so this is a lot. I mean, these integrals, when you're dealing with multiple integration, they can sometimes be really nasty and take quite a bit of time. You need to go through this and be very careful about what you're doing so that you don't make any little mistakes and screw up your whole answer. Okay, so we found the moment now. We found the moment about the x-axis. And again, we're just trying to find the y center of mass here. Now we need to go through and find the mass, the total mass of this object. Okay, so again, let's go back up to this thing and imagine that we're going to find the total area of this thing. We take up a bunch of infinitely small chunks and add them all together. And once we do that, we'll get the total area of this thing more or less. So I want to bring you back to what we did here. In order to define the mass, specifically the little small, infinitely small amount of mass for each of these individual cells, these individual cubes, we said that that amount of mass would equal our mass density times our area. Okay, so we could write this to find the total amount of mass. If we know that the infinitely small amount of mass for one of these little chunks here, dm, equals sigma times dA, then we could basically add up all of these infinitely small chunks of mass to find our total mass. And the way we typically add things up when dealing with infinitely small things is with integration. So to find just our mass here, to plug into this equation here, we're going to take the double integral across the region, or the domain D of our sigma times dA. This expression here we know equals dm, and if we were to integrate dm across all of this region here, we would get our total mass of our object. Okay, now again, what I found is that trying to explain it like this is maybe not what you've heard a ton in calculus classes before, but trying to think of dA or dm as meaning an infinitely small mass or an infinitely small area, it's going to help you a lot in trying to understand conceptually what you're doing in these problems. So we can go through and do this. Well, if I were to plug in what our mass density is, we now have that, or we have a double integral over the domain D of simply y, then dA. Okay, so we could do a similar thing as we did to the previous problem. We could break this up, our domain D, into some bounds across the x-axis, some bounds across the y-axis, and then we have it be an integral of y dy dx. Okay, and as we determined previously, our bounds aren't going to change. We're still dealing with the same shape. So our y bounds would be y equals 0 to y equals 1 minus x squared. And then our x bounds would be from x equals -1 to x equals +1. Okay, so let's go through and evaluate this integral now to try and solve for our total mass. Okay, So we need to start by evaluating this first integral first, and when we do that, we'll get this. We'll have the integral from x equals -1 to 1 of 1/2 y squared evaluated from y equals 0 to y equals 1 minus x squared dx. Okay, this dx doesn't go away. And then if we were to integrate this, or if we were to evaluate, if we were to plug this stuff in like you do when you're taking an integral, I could take a 1/2 out front, it's a constant. I would still have the same bounds, x equals -1 to 1. And if I were to evaluate this again, I would get 1 minus 2x squared plus x to the fourth. Okay, and this would be dx. So now I need to take the integral of this function with these bounds here, and that will tell me my total mass. So if I were to do that, keeping this 1/2 out here, I get 1/2 times 2 minus 4 over 3 plus 2 over 5. That would equal, I believe, 8/15. Yep. Okay. So this number here represents our total mass. Okay, so again, I'm skipping some steps here in the actual solving the integrals. I'm going to leave that up to you. I wanted to just kind of show you how this process would work and how we can kind of conceptually think about the moments and the total mass and how we could use integrals to solve for that. So again, I'm a physics teacher. My degree is in physics. I think there's a lot of beauty in mathematics, but some things in math I might not explain perfectly well. Okay, I like to relate things to more physical situations, being a physicist. So it's hard for me to kind of explain in great detail what all this mathematical stuff means, but I hope you at least got something out of this video, okay, and understanding why the stuff is formulated this way and how we can use double integration to expand on it. Okay, so now that we found the moment about the y-axis, or the moment about the x-axis, sorry, and the mass of the object, we could compute our y-coordinate for our center of mass by just doing our moment about the x divided by the total mass. And we found that the moment about the x was 32 divided by 105. We just calculated the total mass of the object to be 8 divided by 15. If I were to multiply these out, or divide these out, I would get an answer of, I believe, 4/7. Okay, double check if I'm wrong on this, but I think that our y coordinate for our center of mass should be 4/7. So what we found is that the point of our center of mass is, again, our x coordinate of our center of mass, comma, our y coordinate of our center of mass. We determined that this is 0 by symmetry. Okay, this thing is nice and symmetrical about y equals, or about x equals 0, the y-axis, so we can assume that the x-coordinate should just be 0. And then we went through and calculated what the y-coordinate should be. So our position for our center of mass is going to be 0, 4/7. Okay, so again, this is more of a math lesson than a physics lesson for sure. But I do hope, again, that this helped a little bit with your understanding about multiple integrals and finding center of mass. Okay, feel free to come by during my plan or after school or something. We can talk more about this, and I can give you more examples or whatever. Okay, so there you go.